So big questions are: can we build weak solutions that satisfies the energy equality and is the weak solution unique? And these are big open questions. So,
of course, it's just in 2D.
sorry?
Of course, it's just in 2D.
Yes, yes. So in 3D, there are big open questions. People suspect that it's wrong in 3D. The solution would be not unique. There are recent works of Slayer labs that seem to suggest that the solution could be not unique. I don't think Terita was involved, but the lab has a kind of criterion that could be verified numerically showing if the solution is unique or not for some special task of some seminar data. So in 3D, so these are still big open questions, but in 2D, the answer is positive in those cases. Those answers are positive. Those answers are yes. Okay, so I can show you uniqueness. No, uniqueness. Okay, so for lab minutes, I can prove uniqueness in 2D. Proof of uniqueness in 2D. So again, you look at P equal U1 minus U2, and when you perform the energy estimate, what you can show is 1/2 of d over dt of the L2 norm plus mu integral from 0 to t of gradient of d will be less than integral from 0 to t of gradient of u2 d squared. Same as before. There is no integral inside here, no integral inside there, sorry. I get the differentiated form. And this is an integral in space. Same as before. Be careful, now gradient of u2 is far from being in L infinity. It's not even in LP, it's in L2. Okay, so we have to put this guy in L2. So this guy should be in, the square should be in L2, so B should be in L4. Okay, so this is less than the gradient of u2 in L2, the norm of V in L4 squared. Right. And now when you are in 2D, you can use 2D Galliardo-Nirenberg inequality. Which tells you that the norm of V in L4 squared, that's an interpolation inequality, and in 2D it tells you that it's less than the norm of V in L2, the norm of gradient of V in L2. So when I inject this inequality in the differential one, I have this. I have the new gradient of dl2 squared, and then I have the norm of gradient of u2, norm of v in L2, norm of gradient of v in L2. Right? I just replace the x squared on squared by this, and then what I do is I use AB is less than mu over 2a squared plus 1 over 2 mu b squared. Use this inequality, and I say that 1/2 of what we end up with is this, plus the nu becomes a nu over 2. Okay? So I take this for my A. I take this for my B. So I get this less than 1 over 2 mu, the gradient of u2 squared v L2 squared. Forget about this term. What you get in the end is by one-by inequality. You forget about this term. What you get is that v of t in L2 is less than v of 0 exponential integral from 0 to t of the gradient of u2 L2 squared. And okay, this quantity is finite, so everything makes sense. Everything makes sense. And v of 0 is 0. So that's good. But of course, everything should make sense for convalid inequality to apply. So this is very important that here we have this quantity integral from 0 to t of gradient of u2, which is finite. T squared, which is finite. Okay? Okay, so I hope these lectures gave you some the basis about the mathematical theory of Euler and Navier-Stokes. You should not believe from these lectures that existence or uniqueness of solutions is the only concern in fluid mechanics. Far from that. Okay? That's the basics I wanted to teach you because you need to know it. But you must be aware that current research topics in general are quite far away from this because the remaining questions are so hard that nobody dares to tackle them. And so there is a whole part of research into fluid dynamics which is devoted to qualitative properties, asymptotics from one complicated model to a simpler one. So you have many options in the field of fluid dynamics and not only studying the Cauchy problem. Okay.
Do you have any questions from?
Oh, you mean asymptotic time? Oh, well, so you have decay properties due to diffusion. So for a long time, it was not really known how the solution should decay. Now it's known. Then you can look at more elaborated models with temperature, study the long-time asymptotics. That's one thing. I was more thinking, when I was mentioning asymptotics, I was more thinking about models in which you have parameters, small or large, and you try to understand what would be a reduced model, which would be for numerics, which would be more interesting. So trying to derive rigorously some reduced model and something like that. So asymptotic with respect to parameter, not necessarily with respect to time.
Can you, as for 2D Euler, can you mention something about the case that where the vorticity is unbounded? In the case that the vorticity is unbounded, but it is only in LP?
Yes, so for Euler, there are more recent things than Ludovich's theorem. There is this existence of two solutions in LP, something, and the one big result in this area is a result by Delors, who starts from initial data which are only sign measures. So this allows to take into account the original irregular data. And this is tricky. The compactness argument is not so easy when you start from there are also results on weaker notions of solutions by PDEs and Stikeleji recently. It really goes into many directions.